This lecture discusses the mean and standard deviation of sample means. We have mentioned before that the sample mean is random and has a distribution called sampling distribution. Because it is random, we can calculate the mean and standard deviation of sample means. Suppose that a simple random sample x1, x2 up to xn is drawn from a population with mean mu and standard deviation sigma. We can calculate the sample mean x bar. Recall that the sample mean is the sum of the x divided by the sample size n. The slide shows the formulas to calculate the mean and standard deviation of x bar. The mean of x bar is exactly equal to the population mean mu. The standard deviation of x bar is the population standard deviation divided by the square root of the sample size. We can see that the mean of x bar does not depend on the sample size. It is always mu. However, the standard deviation of x bar depends on the sample size. The larger the sample size is, the smaller the standard deviation of x bar is. These two formulas can be proved rigorously using mathematics. Here, we will not discuss mathematics. You only need to understand the formulas and know how to use them. Let's check one example to help us understand the formulas. The population consists of the 5 players on a men's basketball team. We can calculate the population mean, the sum of the 5 heights, and then divide it by 5. The population mean is 80. Consider samples of size 2. The table lists all 10 possible samples. The sample means are also calculated in the table. To get the mean of the sample means, we calculate the sum of all sample means and then divide it by 10. The mean is also 80. Notice that when calculating the population mean, the sum is divided by 5 because we calculate the mean of 5 numbers. When calculating the mean of x bar, the sum is divided by 10 because there are 10 x bars, and we calculate the mean of these 10 numbers. This example illustrates the mean of sample means is equal to the population mean. Now, let's check the standard deviation. The population standard deviation is 3.41. Notice that when calculating a sample standard deviation, the denominator is sample size minus 1. Here, we calculate the population standard deviation. The denominator is the sample size. We can also calculate the standard deviation of x bar. It is 2.09. Here we may notice that the two standard deviations do not exactly follow the formula we mentioned earlier. It is because we are doing sampling without replacement from a finite population. In this scenario, we need a correction factor to the formula. In this correction, the capital N is the number of individuals in the population. It is 5 in our example. The small n is the sample size, which is 2 in our example. In practice, the capital N is usually much larger than the small n. Therefore, the correction factor is approximately 1 and can be ignored. In this example, we want to demonstrate an application of the formulas we discussed. The mean living space for single-family detached homes is 1,742 square feet. The standard deviation is 568 square feet. For samples of size 25, we can calculate the mean and standard deviation of the sample mean. The mean of the sample mean is exactly equal to the population mean. So, mu x bar is 1,742. The standard deviation of x bar is the population standard deviation divided by square root of n. It is 568 divided by square root of 25. The answer is 113.6 square feet. For samples of size 500, the steps are similar. The mean of sample mean is still 1,742, the population mean. However, the standard deviation of sample means is much smaller. It is 568 divided by the square root of 500. It is 25.4 square feet.